Hello, my name is Dr. Jeremy Petrovich, Developmental Editor for Current Protocols at Wiley. It is my pleasure to introduce our speaker, Dr. Mirko Corselli of BD Biosciences, for this webinar titled Providing a Solid Foundation for Simpler and Smarter Flow Cytometry Panel Design. Dr. Corselli has over 15 years of academic and industry experience in the development of flow cytometry applications. He is passionate about driving adoption of cutting-edge technologies through scientific communication. He received his PhD in clinical and experimental hematology and oncology from the University of Genova, Italy. He spent 2 years at the University of Pittsburgh as a research scholar before continuing his research as a postdoctoral fellow at the University of California, Los Angeles. Most of his academic work has focused on the biology and therapeutic potential of human mesenchymal stromal cells. During his tenure at BD Biosciences, he has led the development and dissemination of scientific content showcasing the application of high-parameter flow cytometry in single-cell multi-omic analysis in the field of immunology and immuno-oncology. With that, I turn the webinar over to Dr. Corselli.
Thank you, Jeremy, for the kind introduction, and I would like to thank and welcome everybody that is joining us today. I'm particularly excited to talk to you today about our story on a solid foundation for simpler and smarter panel design, and provide you with tools and information to simplify your panel design process and ensure high-quality data from your experiment. Before starting, I would like to outline and guide you through what we're going to talk today. And we'll start from acknowledging and describing some of the common challenges in panel design. We'll then move forward to describe the benefits of using a 5-laser flow cytometer configuration. And we'll take a deeper dive into spillover, spread, and resolution before introducing the concept of a strategic selection of fluorochrome combinations with minimal spillover to simplify panel design and increase data quality. So I would like to start from acknowledging some of the common challenges in panel design. And we're all aware that panel design can be complex and intimidating at times, because there's a lot of factors that need to be taken into account in order to ensure success of an experiment. We need to understand the biology of our experiment. We need to be able to define a biological tree for a population of interest, understand the level of expression of our markers, and the co-expression patterns of our mark in our panel. We need to understand our fluorochromes. What's the resolution power of the fluorochromes? What about their spillover, spread, and compensation? And what combination of fluorochromes work well together, and which one instead can introduce spillover and some issues? And lastly, we also need to understand our instrument. What configuration do we have access to? How many lasers? What fluorochromes are compatible with my instrument? So there's a lot of factors that we need to take in consideration, but for the interest of the time and for this topic specifically for this webinar, we're going to really focus on spillover, spread, and compensation, and the optimal combination of fluorochromes that can really maximize our results. And the choice of fluorochrome is going to be ultimately also a function of the instrument configuration that we use. So I would like to talk to you just at the beginning about the benefits of using a 5-laser instrument configuration. And 5-laser instrument configuration, the most obvious benefit for using these high complexity instrument is, of course, the ability to design high parameter panels between 18 to 29 plus colors that we can design and execute on this instrument. But today, I would like to talk to you about the different aspect and the different benefit of a 5-laser instrument configuration. And that would be the ability to simplify the design of lower complexity panels between the 6 and 12 color range. And this is enabled by having access to high performing dyes. We'll talk about the brilliant UV dyes and some yellow-green dyes. We reduce spillover. And we will talk about the ability to distribute fluorochromes across multiple lasers and a wider spectrum to minimize spectral overlap and spillover. I will go into this concept in depth before showing practical example of how that translates in better panels and ultimately better biology. So let's start first talking about the benefits of the BUV lasers. The availability of a UV laser allow us to develop a new family of dyes, the BD Horizon Brilliant Ultraviolet fluorochromes, also known as BUV dyes. And we have now 7 fluorochromes that can be detected and used on an instrument with a UV laser. And these bring some benefits because expand the choice of fluorochromes to provide panel design flexibility, but also enable, again, distribution of markers and fluorochromes over an additional lasers. And these fluorochromes specifically have been developed to have minimal spillover across other fluorochromes as well. Another laser out of the 5 laser configuration that I'd like to talk to you about is the yellow-green laser. And the yellow-green laser can be used to detect fluorochromes like PE, PSI 5.5, PSI 7. They conventionally can be detected on the blue laser, but now we can offset them on the yellow-green laser to minimize the overcrowding of the blue laser line. And let me show you just a couple of examples. For example, we're looking here at CD4 stained with BB515, detected in the FITC channel, but much brighter than FITC. And as you can see on the left plot, if we were detecting PE, which is an adjacent detector of the blue laser, we might introduce some spread, as you can see from the width of the positive population into the P channel as compared to the negative. However, if now we move the detection of P off the yellow-green laser, BB515, it's not excited by the yellow-green laser, and therefore we will have no spillover and spread into the PE channel. So that would be already a benefit because we are moving a channel from the blue to the yellow-green and minimize spillover. Similarly, these allow us now to optimize and redesign alternative dyes. For example, the BYG584 is an alternative dye to PE that was strategically designed to be primarily and almost exclusively excited by the yellow-green and not the blue laser. So if you look in this example, for example, on the bottom left, we have CD4 now in conventional PE detected of the yellow-green laser. But it can still be excited by the blue laser, and as such, it will spill into the BB700 channel or the PERC-PSI 5.5 channel and introduce spread. However, if we use now as an alternative the BYG584, now available as a custom dye, you can see that this dye is not excited anymore by the blue laser, and therefore there will be no spread into BB700 channel. So what I'm showing to you are a couple examples of the effort made over the years to expand laser lines and develop new dyes that are more tailored and more fine-tuned to minimize spillover. And the reason why is because spillover introduces spread, and as a result, will impact resolution. So in this example, we're going to show why it's important to minimize spillover. Let's take, for example, an experiment where we want to resolve CD45 array and CD45 RO in a co-stain, 2-stain experiment. And we're choosing first 2 fluorochromes, APC and APC87. On the left, you can see the spectral properties of these 2 dyes, and you may be able to see that the excitation and the emission curve spectrum of APC on the red, a tail of the red will overlap with the detector of APC87, and that's what we call spillover. That will be detected into APC87 channel, will be corrected by compensation. However, the spread that results from this spillover cannot be eliminated. And we can visualize the spread, for example, in the plots that you see to the right of the spectrum. The first plot shows CD45RA APCH7 alone, and we see the single stain, and on the x-axis we have the APC channel, and we don't see spread in that channel. However, when we look at CD45RO APC single stain alone, and we plot against APCH7 on the y-axis, you can see the spread that has been introduced as a result of spillover. That's the larger width of the positive population as compared to the negative population. As a result, when we perform our double stain, it will be really hard to resolve the CD45RA deemed population, CD45RO positive, because of the background of the spread. And that's why spread impact resolution. However, in this second experiment, if we look at the different choice of fluorochromes that we adopted here, we're using BB515 and APC. Now you can appreciate that these are two fluorochromes excited by two different lasers, and their emission spectra are very well separated from each other. So there is no overlap, there is no spillover, there is no spread. And that's visualized in the plots to the right of the spectrum, where you can appreciate CD45RA BB515 on the y-axis when single stain, no spread into APC. Now CD45RO APC, there is no spread into the BB515 channel in the middle plot. And when we perform a double stain with a beautiful resolution of every population and intermediate population. So these are two very quick examples of why understanding spillover and spread has an impact ultimately in biology. And while this would be easy now to remember that we have learned that APC and APCH7, there might be spillover and not between APC and BB515, one of the major challenges now is how can we keep track of all the combination of fluorochromes and what fluorochromes work well with each other with an complicated and ever-growing landscape of fluorochromes. And to address that, we are going to talk about a spread summary. And I'd like to take a couple of minutes just to stop on this slide, and because this is very critical to what we are going to define and discuss in today's webinar. So I really want to take the time to explain this thoroughly. What you're seeing here is a matrix, and is a summary of spread. And we're going to address a couple of questions about this matrix. How was this generated? How do we read it? And how do we use it for panel design? So first of all, to generate a matrix like this, usually you want to stain a blood sample with CD4, a very well resolved and highly expressed marker, in all the possible colors that are available on your instrument. And you can see all the colors in this matrix on the Y, on the column, and on the rows. And there are different ways that once you've run all the single stain of CD4 in all the color, there are multiple ways that you can create several kind of matrices. There are different algorithms, there are different mathematical formulations. We're not going to discuss all of those in the interest of time. I'll be happy to take questions at the end. But just for the purpose of this presentation and this matrix, this was generated by a visual observation and visualization of spread, and then arbitrary assignment of a color, whether green is no spread, yellow is a little bit of spread, and red is significant spread. How do we create this matrix? How do we read it? And let's take, for example, of BV750, like you see in the plots. Now, if you look at the matrix and you look under the column floor, if you look around the middle, you can find BV750. Now we move from that row left to right, and each box will intersect a column on the top in the orange, for example, starting from BUV395, BUV496, and so forth. So you can move along that row, and that is indicating the amount of spread that BV750 introduces into each one of the fluorochromes on the column. So if you follow the green arrow and the white line, you would see, for example, the green box where BV750 intersects BV480 and the corresponding plot where the positive and the negative population, they have the same width in the BV480 channel. So that's what we call no spread. These two fluorochromes do not overlap. There is no concern of spillover and spread. If we keep going to the right, we'll find the yellow box. This is BV750 into BV711. And you can see the corresponding plot where now you can appreciate that the positive population has a little bit more of background and spread into the BV711 detector as compared to the CD4 negative population. And now you move to the red box, and that would be 786. And you can appreciate a corresponding plot where you can see that now the spread it's much more significant, it's much more obvious, and that can have a major impact on resolution. So this is just an example of how we have generated a matrix like this by visualizing spread. And again, it's just one of the ways this can be done. You can also read these in a different way. If I have a marker of interest that is critical and I want to maintain resolution, and for example, it's on my PERC PISA 5.5, I can look at the column on the top. So I'll go on the orange on the top. I can find PERC PISA 5.5, and then I can start scrolling down the column, and I can see where there is red. So where I see red, the red box intersects BUV 737, for example. That would be a watch out that will tell me that my critical marker may be impacted by another marker matched with BUV 737. So this is a summary of spread, but regardless of the algorithm that you use or regardless of the mathematics or the visualization that you use, it has to be understood that this is a reference, it's a guidance for spread, it's not an absolute. There are caveats depending on configuration, the spread can be different depending on instruments, but also there is fundamental understanding that for the same amount of spillover of one fluorochrome into another, the amount of spread may be different as a function of three factors: antigen density, whether the marker is expressed at high level or low level; fluorochrome brightness, for the same amount of spillover, a brighter dye will introduce more spread than a dimmer dye; and instrument configuration. The filter set, for example, that you use in your instrument may have an impact on the amount of spread. For the interest of this presentation, though, I would like just to give an example of the function of spread into, or the function of antigen density into spread. And so this is a simple experiment where we stain ourselves with CD4 PE or CD95 PE. And we're looking at the spread into the PERC PISA 5.5 channel. Now we're using exactly the same fluorochrome. We're using exactly the same instrument on the same day with the same settings. The only difference here is the antigen. CD4 is highly expressed. CD95 is expressed at low levels. And as a function of this, you can appreciate that the spread is much lower when we use CD95 with PE. So again, this reinforces the concept that the spread summary generated with CD4 is a good reference for watch out, because the PE and PERC PISA 5.5 will look like a red box. This does not mean that those two fluorochromes may not be used together. It means it's a watch out. We need additional thought process and understanding of biology in order to minimize that effect. And in this case, we can simply minimize the spread from PE into perceived PSA 5.5 by matching PE with the low antigen expression marker. And this is a concept that we will reiterate later in the presentation. So besides spread and spillover that we've discussed in detail, I also want to remind again that there are other factors critical for successful panel design. We need to understand the biology, the antigen density and co-expression, the fluorochrome, the brightness and the resolution, as well as the spillover and the spread. And we have some rule of thumbs that we usually use for panel design. Match low antigen density markers with bright fluorochrome, and spread only impacts resolution of co-expressed markers. Just last week, Bob Balderas gave a great comprehensive webinar on panel design that touched upon all these critical factors, and I will highly encourage you to have access to this webinar on demand on our website if you didn't have the chance to attend it live. We also have another number of resources on our website and tools to educate you as needed on these critical factors for panel design. But I would really like to move forward now with the presentation and again speak about the impact of spillover and spread in the process of panel design. So we're going to talk about how do we build the panel and how the spillover and spread can really impact our biology. So before getting into the fluorochrome choices and the spillover consideration, as we mentioned, understanding biology of experiment is critical to panel design. So we are going to first define our model system and what biology we are interested in studying. And here it's a 10-color panel that we are developing to study CD8 positive T-cell differentiation. And when we design a panel, we want to create a hierarchy tree like this one that really delineates our population of interest and can guide us on the level of expression and expression patterns of each marker in our panel. So we have our typical lineage markers, CD3, CD4, CD8, to get to the CD8 positive T cells, exclude the CD4. Then we're going to use CD45 RA, CD197, and CD95 as three markers conventionally used to identify differentiation subset of T cells from the naive, central memory, effector memory array. And this is a progression of differentiation that occurs when a naive T cell is presented with an antigen, a recognized antigen that induces activation and differentiation. And then we'll dig even deeper in this subset to study expression of other markers like CD27 and 28, which are expressed at high level in naive state, and they start getting downregulated as cells differentiate. And on the other hand, CD57 and PD1, they are upregulated as cells differentiate toward terminal differentiation. Now that we have the biological information, we can start matching fluorochromes with antigen. And the first experiment and the first example that I'll show you to do, I'll take an approach, and everybody has slightly different approaches, but I'll show you my personal approach and some implication of how we design this panel. My personal approach is always to start from my most critical markers. These are usually the antigens. They're expressed at low levels, and we want to really resolve them as much as possible. So I identify CD95 and PD1 as my most critical markers. And I'm going to use bright or moderate dyes like P and B711 to make sure I have enough resolution power to resolve these markers. So I'm primarily focusing just on matching antigen density with fluorochrome brightness. And in this example, once I've secured my good dyes for my critical markers, I'm adding now all the other remaining fluorochromes and matching with the remaining antigen randomly. I'm not paying attention to any implication that could come from spread from any other fluorochrome in the panel, because I'm relying on my first choice of bright dyes for my critical markers. So just pick whatever in the fridge, what's available, I put them randomly, and I run with the panel. Now let's review the panel. And again, let me just take 1 minute to guide you through the data analysis and how we assess the quality of this panel. On the top row, we are looking at the gating strategy. We gated first on lymphocytes and CD3 positive T cells, and now we gate on CD8 positive. If you look at the arrow that goes to the right, the next plot. Again, we're going to use CD45 array and CCR7, CD187 to identify central memory, effector memory array cells. From the double positive, we can also use CD95 to discriminate naive and central memory and stem cell memory T cells. From the CD8, if you follow the arrow that goes above the plots, you can see now we're looking at CD27 and CD28 or CD57 and PD1 within total CD8. And when you can see those red X's there, it's because you can already appreciate that you don't have a good resolution of these markers. You can barely distinguish different subsets that we know exist in this population. Everything is kind of merged together. Really hard to say what's positive and negative. And if you look at the row below, the second and the third row, that's when we go a level deeper. So now we're looking at CD27 and CD28 within each subset of differentiated T cells. And this is the beauty of flow cytometry, because it allows us to do this level of depth and deep analysis. And again, you can appreciate that we have a fairly poor resolution of all of these markers. So I'm going to focus just on one marker, and we're going to break down basically what went wrong and why, for example, we were not able to have a good resolution of PD1 despite having used a good dye like BV711. So let me break it down in this slide, and I'll guide you plot by plot. The first plot, we're analyzing PD1 single stain. So we're only looking at total cells, and we're looking at PD1 BV711. And as you can see, this is a critical marker because it's expressed at very low level, what we usually define as a shoulder. It's not very well separated. It's very low level, but we can definitely pull the population out with BV711. And we can assess roughly 13% of cells are positive. The second plot is our full panel minus PD1 BV711. So this panel has 9 antibodies. We're just not including BV711. And this control, also known as fluorescence -1 or FMO control, it's used in this case to properly set the gate for our real signal for 711. And as you can see, now the gate is shifted dramatically to the right because it indicates that there's a lot of background, a lot of spread that is forcing us to move the gate to the right. And the result of that, when we now deserve the full panel, this includes also PD1, we will be measuring basically no positive cells for PD1. And that's because the real signal has been confounded and buried in the background that we assessed. So why did this happen? And what went wrong? And to determine what went wrong, we are going to go back to that spread matrix. So focus for now on the matrix on the bottom. So while we're looking now at the matrix for this panel, you can see every specificity under floor and every specificity in the column on the top. Now, remember, we can assess, for example, we can interrogate for PD1 BV711 in the orange box. If we consulted this matrix before designing the panel, we would have noticed that, for example, going down in the red box, you can see the red box surrounding the dark red box, you will notice that BV700 does introduce a significant amount of spread into BV711. So we chose BV711 first, and then we added all the other fluorochrome randomly. We didn't take in consideration that BV700 will have had an impact on the resolution of PD-1. And to confirm that, if you now look at the fourth plot on the top, this is the full panel minus now CD8 BB700. This is another way we use FMO controls, is to understand and discover who was the fluorochrome that introduced a spread. And you can see that now that we have removed just one fluorochrome, BB700, so this is a cocktail with 9 antibodies, we have restored the real population of PD-1, and we can see now 10% of the cells. So this really confirms that, as predicted by the reference spread matrix, we have introduced a spread by using CD8 BB700, and that had a significant biological impact on our panel. So just as a summary of this part of the panel design, the process that we use, we matched bright fluorochrome with critical markers to ensure resolution, and that's a very good first step. However, the spillover from all the other fluorochromes that were subsequently added to the panel was not taken account. And as a result of that, we lost biological resolution. So it really brings the point that it's critical to understand the impact that each and every fluorochrome in the panel has on each other. And that's where panel design can become complicated and complex, because you need to be able to keep track of all the possible combinations. And that brings us to the last part of the webinar, that it's the tools that we want to share with you and provide with you to really minimize this challenge of panel design, minimize the risk of making a wrong choice of fluorochrome that will have a significant impact on our biology. So what I'm going to talk to you in the last section of the webinar is a strategic selection of foundation fluorochromes with minimal spillover between each other. This approach simplifies panel design because it reduces the number of challenges and the strategies needed to overcome the impact of spread. Minimizing spillover and spread also ensures higher quality data because we are removing background. And what is really important to understand is that the number of foundation fluorochromes is a function of instrument configuration, the number of lasers and detectors that we have, and as I will show in a couple of slides, the higher the number of lasers, the higher the number of foundation fluorochromes, which brings us back to the benefit of a 5-laser configuration. So we are going to compare here, for example, side by side, a 3-laser configuration on the left, which usually can take us up to 12 colors, and a 5-laser configuration on the right. Now, you can remember that we talked at the beginning the ability to spread fluorochrome across different laser lines. And that's because on a 3-laser, we can overcrowd a little bit the laser lines to fit 12 colors. And this slide shows exactly that ability to spread fluorochrome across different laser lines to minimize spectral overlap. So on the left, we can see we have 3 lasers, and we can start really narrowing down on fluorochromes that are spaced out across different lasers, across different areas of the spectrum, and they minimally overlap. As a result, there will be no spillover or minimal spillover and minimal spread. On a 3-laser blue, violet, red configuration, we can find 6 of these colors that work very well together without additional issue. If we move to the 5-laser configuration on the right, by virtue of having 2 more lasers and a wider spectrum available, starting from the near UV now, we can reach up to 10 colors with minimal spectral overlap. And just for your reference, this is a table where we provide an example of foundation fluorochromes. It's really important that we highlight that, again, this is very much related to the instrument configuration. It depends on how many detectors you have, how many lasers you have, what filter set you have. But these are just examples in the instruments that were available to us and that work for our experiment. But the concept stays for every instrument you can identify a perfect combination of fluorochromes that minimize the spillover. And again, just to put it back in the context of spread, which ultimately is what we're really interested in, you can see here, this is our 5-laser 18-parameter fluorescent parameter instrument. And when we look at the full matrix on the top, it's an 18 by 18, you can see that there's still a lot of areas where there's a lot of red. And this means that if we choose our fluorochrome randomly, there is a chance that we might choose some fluorochrome combination that have high impact on each other. But now what we're doing, as you see at the bottom, we are strategically narrowing down to 10 fluorochromes for which there's very little spectral overlap and spread. There's no more red. There are only fewer spots in yellow that indicate potential impact due to spread. So really, we are starting from a better starting point. We minimize areas of challenges and minimize areas of potential mistake and loss of resolution. So now when we redesign the same exact 10-color panel on the same exact instrument, this is the same configuration, the same instrument, but now we are taking in consideration the spillover and spread before designing the panel. And we can use a similar approach. So we still start from our more critical markers. So we use PE and B421 as very bright dyes that can ensure resolution of our critical markers, C95 and PD1. We can also confirm now that if you look at B421 on the matrix above, and you look from the orange B421 box all the way down, no one of the other fluorochromes introduces spread into B421. So there's no risk there. Same for P1, we can see that there's some potential risk on BUV615. Other than that, all the other fluorochromes do not impact PE. But again, we're going to use these as a guidance, as a reference, and it tells us there is a watch out. So the next step is to take care of those watch outs for the other markers. So where, for example, can we use BUV615 now to make sure that it does not impact other critical markers like PE and PSA7? So we are now using PSA7 on CD28 and other critical markers. And now we're using BUV615 strategically. We match it with CD27. And the reason why, if you remember, we talked that the spread is a function of antigen density. This matrix was generated using CD4, which is much, much brighter than CD27. So by virtue of using now BUV615 with CD27, a lower antigen density marker, we have confidence that this is not going to be a problem for P and PSA7. Again, this reference is generated with CD4. And we can go forward with other markers. There are other watch out that we can take in consideration. For example, BE480, we know that can introduce a spread in BUV615. We match it with CD45 array. We are taking in account that BUV615 is a bright dye, so we'll overcome the spread. It does introduce a spread, for example, on BUV486, and we need to be careful of that. We are using the safe APC for CD197. Again, from our matrix, we can see APC is clean in every direction. And then to finish, we just put our dim dyes, very clean dyes on our lineage marker express a high antigen density. So we're taking consideration here everything. We're taking consideration the spread, the spillover, the antigen density, and the level of expression. Now, when we review the panel, you can definitely appreciate on the top that we have significantly increased the resolution of our markers. And we have a beautiful separation of all possible subsets of CD27, CD28, CD57, and PD1, either on total CD8 on the top as well as each and every subset on the bottom rows. And just to emphasize again how the better selection of fluorochrome from the same exact instrument can have a significant impact on your biology. We're going to compare side by side. On the top was the first panel where we didn't pay attention to spillover and spread. And the bottom is the panel where we strategically selected upfront fluorochromes with very minimal spillover to simplify the process, and most importantly, do not run into mistakes or problems that will have impacted biology. So you can really see the stark contrast between the two. This is for CD57 and PD1. The same you can appreciate for CD27 and CD28. So it's not only about making the process simpler, which is definitely important, but ultimately it's about the biology and the accuracy of your results and the quality of your data. And this is something that you can achieve, again, with the 5-laser configuration and taking full advantage of UV dyes and better dyes to really spread out across the 5-laser and get the level of resolution. So just to conclude the webinar, what we have discussed is that at the high level, we have acknowledged there are several factors that contribute to the complexity of multi-color, multi-parameter panel design. There's the biology, the fluorochromes, the instrument. Overlooking every of these aspects has an impact on the quality of the data and the results. But for this webinar, we really focus on spillover and spread and how can these affect panel resolution. We've also discussed how higher capability instrument, 5-laser configuration, allow for use of new dyes with reduced spillover, and how these also allow to simplify panel design by selecting fluorochromes with minimal spillover between each other. It is very important to remember that even though the process has been significantly simplified by strategic selection of these fluorochromes, there are still fewer areas of potential mistake that needs to be taken account. Ignoring those watch out that you must still have will still have consequence on the panel. So that's why it's really important that to have the foundation of panel design, understanding the rules, but in this context of a selected combination of fluorochrome, there are very few areas where those rules need to be taken account. And also the last note is again that the foundation fluorochromes that I presented today are examples for given configuration. There might be difference across different instruments, but what we want to really emphasize here is a tool and a thought process. Understand your fluorochromes, understand your instrument. You can create, if you want, and be happy to discuss that, your own matrices and really narrow down on the best combination and optimal combination of fluorochromes for your instrument and for your assay and for your biology. And with that, I would like to acknowledge part of the team that's been involved in the generation of this content and this data. From the data generation, the application team in the scientific affair team at BD, led by Stephanie Widman, Bipul Endujena, Chet Sisolantong, and Saloni Desai, and our marketing team for concept and design, Caroline Chang, Adam Best, and Bob Baldera is critical and fundamental for design, experimental design, and concept. And of course, I want to thank you all for your attention, for giving your attention and your time today. And I'll be very happy to address any possible questions you may have. Thank you so much.
Thank you, Dr. Corselli, for that presentation. One of our first questions is somebody for the audience would just like to clarify, what instrument is this panel for, and can it be applied to any instrument?
Yes, thank you for the question. We didn't specify the instrument here. It was a BD LSR Fortessa X20 instrument with 5-laser. However, the concept really applied to any flow cytometer. So This panel could be run on any flow cytometer, whether it's BD or not BD, that is equipped with 5 laser and has compatible filter set configuration. As we mentioned in the presentation, however, the foundation fluorochromes and the spread matrix may change from instrument to instrument. So that there will be always a good option to characterize your own instrument of choice. But having said that, what I really want to emphasize is that besides slight difference between different instruments, some core concepts and combinations will apply to virtually any flow cytometer. We know, for example, that the first fluorochrome of each laser line, if you use the combination of this first fluorochrome, you will have very minimal to virtually no spillover. So under a 3 laser configuration, regardless of the instrument, your B421, FITC, APC, those 3 will be extremely clean. Now, if you move to any instrument with 5 laser, BV395, B421, FITC, PE, APC, you start already with 5 combinations. They're very clean, irrespective of the instrument. You then move to the far right of the spectrum and you start adding great dyes like PSI7, BV750. Those combinations very likely would be clean and have minimal impact, irrespective of the instrument. It's when you start moving to higher dimension, start getting to the 8 and 10 color space, and you need to fill the center of the spectrum where some variation between instruments can occur. And that's why the value of having BUV dyes with very clean dyes like BV496 or BV615, or even BV480, which is another great dye that in every instrument will have a very minimal spillover into these foundation colors.
Great, thank you. So considering that spread summary table, is this a table that's available if somebody were to email you? Could they receive a copy of it?
We can share the spread metrics, and we are actually planning to share with the attendees a collateral where this panel will be showcased as a PDF. So you get a reference of the dyes used. We also showcase a 6-color panel on a 3 laser with a selection of 6 optimal colors for 3 laser and the corresponding spread matrices. However, I really want to reinforce that this is not an absolute metrics, and this really applies to our instrument. The recommendation would be to have instrument-specific metrics ultimately performed on a individual instrument. But we can share it as a reference with the understanding that there might be variation depending on how the instrument is set up, the lasers, the laser powers, the settings, and so forth.
Great. So one question that has come up is the use of FITC, and one of the audience members was asking if FITC is considered a dim fluorochrome.
Yes, FITC is one of the possibly dimmest fluorochromes in the portfolio of dyes, and this is for any dye. But I would like to emphasize that this doesn't necessarily mean it's a bad dye. There's an advantage of having a dim dye. It's dim, but it's extremely clean. It has very little spillover and spread into other detectors, and it receives no spread virtually from any other fluorochrome. So it's an extremely clean dye. And as you may have seen in our panel, we used FITC for our lineage markers, CD8. And that's where I would strongly recommend to use FITC. Any lineage marker, CD3, CD4, CD8, CD19 for B cells, CD14 for monocytes. These are markers that are very well expressed, and they are the top of the biological hierarchy. It means that ideally they could influence every other marker below down the hierarchy tree. So you want something very clean, and bright enough to resolve these markers. So FITSI, it's a fantastic choice for these kind of markers.
Great. So if someone wanted to learn more about compensation in flow cytometry and some characteristics of fluorescence colors and the markers it use, what are some of the best available resources?
So we have a lot of resources on our website. We have a dedicated microsite on panel design education where you can find a lot of webinars, presentation. We have tips and tricks and videos, and a lot of materials that really can educate on those fundamentals of compensation and really understand a little bit more in detail about the property of fluorochromes. So I will highly encourage you to go on our website and look for a microsite on panel design education. We can provide, if you reach out, we can provide the link or any information that might be required.
So revisiting that spread summary matrix, how can somebody go about creating a matrix like that using their instrument?
Yes, thank you for asking again the question so I can clarify further. There are multiple ways that that matrix can be created. The first step will be to generate data by running CD4, staying with all available fluorochromes for that instrument. And once that experiment has been done, data needs to be analyzed, and the spread into the detectors can be measured in multiple ways. So now if you use FlowJo, there is an automated way that once you analyze your data, you set your gate on the positive and negative for CD4 in the fluorochrome, it can automatically calculate what's called a spillover spread matrix. And generate some values that can be that will be a function of spread. That's a mathematical way. There are other functions, other calculations that can be done, or like we did in the case of this webinar, we decided to go with the subjective visualization of the spread. So we basically look at the single stain of CD4 in all the color and looked at the spread into all the channels. So it's a bit of manual work, but there are two advantages of these. You can visualize the spread rather than relying on a number, but you can also learn and become familiar with the fluorochrome combination that work well together or they don't. So I really encourage everybody that want to learn more to do that exercise and spend some time looking at every plot into each and every detector to really become more familiar with this combination and identify visually what the spread is. But there are a number of resources, again, a number of algorithms that can create a similar spread matrix.
Thank you. When is it recommended to run fluorescence -1 controls? And can I run them only once at the beginning of my study?
Yes, that's another great question. The fluorescence -1 control, as I showed, are fundamental really to understand the performance of a panel, to assess whether we have lost resolution or not when we compare, for example, to a single stain like we did, or to identify where the loss of resolution came from. What was the fluorochrome that was responsible for the loss of resolution? Now, of course, the FMO controls require a little bit more work because you need to run more tubes. However, it's a very critical part of the assay development. Having said that, once you run your panel, you define your panel, you run your FMOs, you're happy with the level of resolution, you don't need to run the FMOs for every experiment moving forward, with the only caveat that if you change the biology, for example, you validated the FMO on resting cells, and then you want to run activated cells, that you're changing the biology, then you're changing potentially levels of expression. In that scenario, I would recommend to run the FMOs again. But if you're keeping the conditions the same, you can run the FMO only the first time to validate and assess the panel.
Spectral flow cytometry enables detection of more fluorochromes per laser. Would that result in more foundation fluorochromes on a 3-laser configuration?
Yes, so that's another very good question. So it is true that spectral flow cytometry allows to detect more colors per laser. For example, on a 3-laser spectral flow cytometer, we can detect up to 20-25 colors. And this is because the way spectral flow cytometry works allows you to detect simultaneously dyes that are very similar to each other, like FITC and Alexa Fluor 88 or BB515, or APC and Alexa Fluor 647, which we cannot do with conventional flow cytometry. Having said that, spectral flow cytometry does not elude the fundamental rules of spectral overlap and spread. So the moment you use highly overlapping dyes like Alexa 488 and FITC, you will have a lot of spread. So it doesn't necessarily increase the number of fluorochromes with less spillover. If anything, you're using more dyes, but you're going to have to deal with more spillover and spread due to the high similarity between these dyes.
Thank you. So could you just elaborate a little bit more why some fluorochromes cannot be used with other fluorochromes?
Oh, excellent question. And just to clarify, I would not say that some fluorochromes cannot be used with other fluorochromes. Virtually all the fluorochromes can be used in a panel. When you see a red in a matrix for 2 fluorochromes, that does not mean that the 2 fluorochromes should not be used together. It means it's a watch out. It means be careful because there is spillover and potential spread. However, there are strategies that we can use to work together these 2 fluorochromes. And I can just give an example. Let's say you have 2 fluorochromes that spill into each other, and we show the example of BB700 and BB711. Now, if I want to successfully use these 2 fluorochromes in a panel, I need to take in consideration the spread and the spillover, and then I need to take in consideration an additional layer of information, which is the biology. So, for example, if I now use CD8 BB700 and CD4 BB711, as we know, in peripheral blood, CD4 and CD8 are not co-expressed. So there is not a double positive population. And spread is only relevant when you analyze co-expressed markers. So in that case, we could perfectly use BB700, BB711 by virtue of the markers not being co-expressed. So there will still be spread, but will not affect biology. Another way that you can overcome the spread if you really have to use these 2 dyes, instead of using BB700 on a very bright, highly expressed antigen like CD8, you can use on a very dim marker, on a very low expressed marker like PD1, and as I showed, that will reduce the spread, making more compatible with BB711. So just to summarize, when you have 2 fluorochromes that have high spillover and spread, that doesn't mean you cannot use them. It means you need to think more about strategy to make them work together. And the approach that we show today is an approach that we simplify panel design because we eliminate upfront those challenging combinations, so you don't have to think that much anymore about the strategies.
Well, thank you. We've unfortunately reached the end of our time today for questions. I'd like to thank Dr. Mirko Corselli of BD Biosciences for taking the time to present to us his talk on the foundational principles underlying flow cytometry panel design. Any questions that were not addressed during this question and answer session will be answered by email. This presentation was sponsored by BD Biosciences in partnership with Wiley's Current Protocols and will be available for on-demand viewing on the Current Protocols website at www.currentprotocols.com in the webinar section under the Resources tab. Thank you for attending.